This is a presentation for Computing 354, Group 25, Groceries. In this group, our members consist of Andy, Brendan, Harit, and Yogesh. In this demo, we are primarily going to be demonstrating implementation of SQL queries within our project. Additionally, instructions to run the program will be found in the README file included in this program.
For one of our join queries, we applied an equal join to the store order and customers table. This is so that when a user logs in and navigates to the order history page, we can display their first and last name, in addition to other order details such as order ID, cost, order time, and payment method.
In addition to Yogesh's join, we're using another type of join here, namely an inner join. The purpose of this join is primarily to circumvent a MySQL error code that prevents modification of a table that we use select on. We bypass this by using an inner join to join a table with itself to allow users to increment the products that are in the shopping cart. The inner join is only activated when the product is already in the shopping cart, and if it isn't, then we would add a new tuple to the shopping cart. We can see this here where quantity is increased, and if I add, let's say, a fruit of a peach that is already here, the number will go up, and we'll increase an existing product in here. Additionally, as you may have seen earlier, we have something called healthy choice, and healthy choice utilizes a division query to essentially check when a user meets all the requirements, which is specifically that they have every type of food group in their shopping cart. This is employed by using a not exist, not in division query to firstly select all customers with shopping carts that fulfill this condition. The additional select count up here with a where condition returns a Boolean that checks whether or not the current user that is logged in is within this list that we use the division query for. When the user fulfills this condition and a 1 is returned from this query, we display a healthy choice symbol to indicate that the user has every food from every category in their shopping cart. And we can see this here if we delete a type of category. So now we don't have every type of category and it's missing.
So next to the shopping cart on the nav bar, there's a number that shows how many items are in the shopping cart. So when you add to cart, the number would increase. This is done through a sum aggregation query that sums over all of the items in the shopping cart of the user.
To provide an overview of each category and how many items are in each one, we have a general overview that displays each category name and the respective count, grouped by their category name. This is using an aggregation with group by using count, and we can see it here in the code, and this is what it looks like with its respective number of items in each one.
I'll be going over our delete operation with Cascade implementation. We've given users the ability to delete their account, which has been implemented using a delete query in Python. From the SQL dump, you can see that this deletes the tuple corresponding to their user ID in the user relation, cascading into any relations which contain user ID as a foreign key, such as customer, for example. I'll demonstrate this by deleting the current logged in user with user ID A123. After the deletion, the user ID A123 and its corresponding tuples no longer exist in the database. I'll now demonstrate our implementation of update queries. We have multiple update queries in our Python code, which allow users to update their account information, such as first name and last name. I'll demonstrate this by changing user B123's first and last name to test. As you can see, it's been changed on the web page. And in the database, the customer relation now contains the updated first and last name for user B123.
So the way we implement assertions to SQL is actually by triggers. And whenever a semantic constraint is violated, then we throw an error and we set the message text to be the error message. And in Python, it's appropriately handled. If I go to the exception, then it flashes the error. And for a quick example, let's say I go to sign up form, I do something for username, but have an empty password. If I try to sign up, then it'll flash this error.
Another application of the trigger is applied in our application through automatic primary key generation. We applied this concept to the store order and shopping cart tables. For example, for store order, when a user places a new order, what we do is we go to the store order table, get the max of the order IDs, increment this by 1, and set this as the order ID for the newly created order.
So one way we thought about database security is by preventing SQL injections. So right now, we're using database API to parameterize our string inputs, and this automatically escapes all the characters from the input. So for example, if I go to the category page, as I try to inject this query in, that would select all the tables, all the items from the table, it shows nothing. But let's say I use this unsafe method, which doesn't use parameterization at all. If I save here and then I run it, well, we would select all of the categories. So that'd be a pretty bad injection. And you could see how that could extend to even more malicious code being executed.